delta G of reaction, delta H of reaction, delta S of reaction, and formation reaction is going to be the topic of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also offer MCAT, DAT, and OAT prep as well. I'll leave a link in the description for where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified when I post the next one, subscribe to the channel, click the bell notification. All right, so formation reactions here and calculating delta G, delta H, delta S. So we're going to get into some math here, but it's going to be very plug and chuggish. So it turns out the back of your textbook's full, oftentimes, of an appendix with thermodynamic quantities in it, usually delta G's of formation, delta H's of formation, and molar absolute entropies. Now, in the case of a molar absolute entropy, it turns out those are convenient. We don't usually use formation reactions for entropy. So, and to calculate, the entropy change in a reaction, it turns out it's just going to be products minus reactants. So you could do this with, say, the change in your net wealth, before and after visiting a casino. Let's say you walk into a casino with $100 and you walk out with $500. Well, if you walked in with $100 and then you walked out with $500, you and I can both easily see that, yep, your net worth went up by $400. That's a change of positive 400. And notice you get that by doing final minus initial. The final state, I had $500, minus the initial state, I had $100. And 500 minus 100 was positive 400. Well, instead of talking about money, we can talk about exactly how much entropy the reactants and products have. And if you just do products minus reactants, i.e. final minus initial, you'll get there. Now, it turns out we can't do the same thing for delta G and delta H, though. So it turns out we never really know how much G gives free energy or how much H, enthalpy something has. We can only ever measure changes. So for example, let's just say I told you I went on the South Beach diet and I lost 50 pounds. And then I got off the South Beach diet and I gained back 60 pounds. And then I went on the Atkins diet and I lost 30 pounds. And then I got off the Atkins diet and I gained back 50 pounds. And then I went straight up keto and lost 100 pounds. And then I got off keto and I gained 60 pounds back. And so how much do I weigh now? Well, you don't know because you never knew what I started at or anywhere along the way. If you had a reference point, either my initial weight or my weight at any point in time along the way, then based on the changes, you'd know my weight at every one of those points. But we don't have a reference point. I never told you that. So, and it turns out for Gibbs free energy and enthalpy, that's exactly the case we have. We can measure changes in free energy and changes in enthalpy, but we don't have a reference point. But that's not true for for entropy. For entropy, we have a reference point based on the third law of thermodynamics. So it gives us that reference point. So for a perfect crystal at 0 Kelvin, it has 0 entropy. That's our reference point. And we can calculate entropy changes and starting with that point and then starting from there and changing from there. But having that reference point, we're at 0 Kelvin as a perfect crystal is 0, I'll then can figure out what the entropy is of any substance under any condition having that reference point. So that's kind of the idea. So we're going to end up using these formation reactions for delta G and delta H. Turns out you don't actually know even what a formation reaction is to use them, to do the plugging and chugging. Somebody designed them in just such a way that if you just simply do products minus reactants, just like we did with entropy, that you're going to calculate the delta G and delta H of the reaction. So the math is great here. It's just products minus reactants, and you don't even have to understand where the equation comes from. However, because we've introduced these, we often talk about what formation reactions are, and we want you to recognize what a formation reaction looks like. And we'll talk about that at the end of the lesson, but just keep in mind, you don't actually have to understand that to do the math here, but you will probably need to understand it because there's some other questions we might ask you in recognizing these formation reactions. So now let's do some plugging and chugging for a reaction using the provided data here. And again, it's just going to be products minus reactants, and you just have to use the appropriate column. So if we first want to calculate delta G of the reaction, then we'll just use the column with the delta G's of formation. And again, it'll just be products minus reactants. But notice the delta G of formation for Cl2 gas here has not been provided. And we're going to fill in that box right there on your study guide. And so it turns out for any element, notice all the other species were compounds, but for any element in its standard state, it turns out its delta G and delta H of formation values are 0 by definition. When we talk about what a formation reaction is, we'll see why that is. but they're zero by definition, and you have to remember that. So they don't have to supply them for you, these delta G's and delta H's of formation, for elements in their standard states, but they do have to be in their standard states as well, because you should know that they're zero. We expect you to know that now. So notice for chlorine, chlorine is a diatomic in its standard state, and it is a gas in the standard state. If this was like chlorine gas, just Cl gas, not Cl2, it would have a number. If it was Cl2 liquid or Cl2 solid, then these would have numbers. But because it is an element in its standard state, the delta G and delta H of formation are zero. Notice your absolute entropy is not zero, because again, the only time something has zero entropy is if it's a pure crystal at 0 Kelvin. All the thermodynamic data in this table were from 25 degrees Celsius, not 0 Kelvin. All right, so now let's do some plugging and chugging, products minus reactants. The N and the M here that you see are just meaning that you got to multiply by the coefficient for that particular species. And so in this case, the products are Cl2 and it's got a 3 in front of it. So we'll take 3 and times 0 in this case. And then plus the value for pH3 is 5.4. And then we'll subtract off the sum of all the reactants. And in this case, we got PCl3, whose value is negative 288.1. Plus 3 times HCl's value, which is going to be the negative 92.3. Cool. One thing to note, a lot of times students will sum this up and get a negative number, and then when you subtract a negative number, you end up adding. Be careful on your signs. Let your calculator do the work for you here. So 3 times 0 is 0, so 5.4 minus, and then I'll put a big fat parentheses right there, negative 288.1 plus 3, that's not a 3, 3 times negative 92.3, and I'll end my parentheses, and we're going to get 570.4, and that's a positive number. So, and that is going to be in kilojoules. And then we'll calculate delta H of reaction next. And it'll just be products minus reactants, but using the delta H's of formation instead. So in this case, once again, we're going to have 3 times 0. So for the Cl2, yet again, and then plus 13.4 for the pH3. Minus PCl3's value is negative 269.6. Plus 3 times HCl's value, which is negative 95.3. Cool, and we'll let our calculator do the work for us once more. So 13.4 minus parentheses, negative 269.6 plus 3 times negative 95.3, and I'll close my parentheses, and we're going to get 568.9. And again, that's going to be in kilojoules. And then finally, we'll calculate delta S of the reaction using the absolute molar entropies there. And so again, products minus reactants. So in this case, instead of a 0, we're going to have 3 times 223 plus the value for pH3, which is 210.2. And then subtract out all the reactants. So PCl3's value, 311.7. Plus 3 times HCl's value of 186.7. And once again, we'll let our calculator do the math here. So 3 times 223 plus 210.2 minus parentheses, 311.7 plus 3 times 186.7, and my parentheses, and it turns out, no, I definitely needed those parentheses. 7.4. Really small number here. And if we look at our units, it's not kilojoules, it's now joules per Kelvin here. So delta G and delta H both given in kilojoules, but delta S just in joules per Kelvin, as it turns out. Cool, and that's our plug and chug calculations. Now, one thing to note, I have seen this show up a time or two on an exam where they'll still give you the delta H's of formation and the absolute molar entropies, but they won't give you the delta G's of formation, but still ask you to calculate this delta G at a given temperature, usually like 298 Kelvin, 25 degrees Celsius. And what they're actually expecting you to do is to still go back and calculate delta H and delta S, and then to go back to your get higher test scores equation, and they want you to plug your delta H and your delta S and the temperature they want delta G at, in this case 298 Kelvin, back into this equation and solve for delta G. It really sucks. But again, you got to be careful on your units. The delta H and the delta S have to both be in joules or both be in kilojoules. If all of your delta G's are in kilojoules that you're solving for on a multiple choice, well then by all means put your delta H and delta S both in kilojoules. And that would mean for delta S, instead of 7.4 joules per Kelvin, it would be 0.0074 kilojoules per Kelvin before you did your plugging and chugging. So just keep in mind, I have seen it show up that way on an exam. My apologies if it does, because that's about the worst it could be. But outside of that, it really was just plug and chug, products minus reactants for any one of these three thermodynamic quantities. Cool, so that is the math of this, but now we've got to talk about what in the world a formation reaction is, and I'm going to need a little room for that. So now we'll talk about what these formation reactions are, but once again, all the plug and chugging you just did, you didn't have to understand what a formation reaction was to do it, just products minus reactants, plug and chug. However, so we might ask you to actually recognize what a formation reaction looks like on a multiple choice question. We might give you, 5 choices and say, which of the following is a formation reaction? Well, if that's the case, then we've got a little more work to do. So it turns out a formation reaction forms 1 mole of a single product, and the reactants are all elements in their standard state. So like, if we take a look at, say, like HCl, when we had the formation reaction for delta G of formation, delta H formation for HCl, what it means is that we had the delta G for a formation reaction or delta H for the formation reaction of HCl. Well, if it's the formation reaction of HCl, then we're going to form exactly 1 mole of HCl. And that HCl could be solid, liquid, gas, whichever one we want to talk about. The table is talking about HCl gas, so we're going to form 1 mole of HCl gas. But the key is then on the reactant side, you can only have elements. You're not allowed to have any compounds on the reactant side and still have it be a formation reaction. So the elements that make up HCl are H and Cl. And then finally, those elements have to be in their standard state. And by standard state, that is going to include things like solid, liquid, gas, but also like your 7 diatomics are diatomics in their standard state as well. So you got to know those as well. So as far as solid, liquid, gas, if you've got a periodic table like the one I've got here, that's pretty common. So everything in black is a solid in the standard state. Everything in red is a gas in the standard state. And there's only a couple of liquids. And then the truth is, most tables are only going to include bromine and mercury as liquids. This one's got gallium and cesium and francium. So, and their melting points are kind of close to room temperature and stuff like that. I'm not going to get into it. But for you, the one you're likely to see is probably just mercury and bromine being liquids in the standard state. Several handful of gases, including hydrogen over here, and then everything else is going to be a solid. And then finally, know your 7 diatomics. 6 out of the 7, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, form the number 7 on the periodic table to take the shape of the number 7, and then hydrogen is the 7th one. Or if you prefer the mnemonic, never have fear of ice cold beer, then take your pick. But you do have to know your 7 diatomics. They are diatomic in their standard state. Cool, so then the standard state of hydrogen, it's diatomic and it's a gas. And then chlorine is diatomic and a gas as well. And then finally, you got to balance this. And notice normally to balance this, what we'd be tempted to do is we'd be tempted to put a 2 over here so that it's balanced, but we can't do that here. So because again, a formation reaction forms exactly 1 mole of a single product. If I put a 2 in front of HCl, it's no longer technically considered a formation reaction, so we can't do that. And so if you're going to be stuck with fractions because of diatomics and things of this sort, you're just going to be stuck with fractions. And so we're going to put a 1/2 here and a 1/2 here. And if you're really dead set against on not having fractions, well, then use decimals and put 0.5 and 0.5. But you can't just double it through or it's technically no longer a formation reaction. But the delta G of this reaction right here is negative 92.3 kilojoules. The delta H of this reaction right here is negative 95.3 kilojoules. That's how those formation reactions work. Cool, so now we know how to recognize the formation reaction. So I might just say, hey, which of the following shows the formation reaction for solid sodium bicarbonate? Well, solid sodium bicarbonate, if I'm doing the formation reaction, then solid sodium bicarbonate has to be the product, and that's NaHCO3, and I'll form exactly 1 mole of it. And then what do I form it from? Well, from all the elements that make it up in their standard states. And so in this case, it's made up of sodium and hydrogen and carbon and oxygen. And now we got to put them in their standard states. And so in this case, sodium is just a solid, like the vast majority of the metals. Hydrogen's diatomic and gas. We'll skip carbon and come back to him. And then oxygen's also diatomic and gas. But carbon is special. So, and he's probably the only special one you have to know, but I also include sulfur on there as being special. But carbon has multiple solid allotropes. And so if all you did was put solid right here, technically it's not sufficient. Now, some professors don't want to get lost in the weeds and don't want to kind of go through this crazy detail, and they'll accept that. However, some are sticklers and they want like what's technically correct. And so because it turns out that there are 3 allotropes of solid carbon. There's diamond, there's graphite, and there's something called Buckminster fullerene. Well, it turns out the lowest energy and most stable form is graphite, and that ends up becoming the standard form then. And so as a result, it's not just enough to put solid, you've got to tell me which kind of solid carbon. In this case, we'll put solid graphite. If it says solid diamond, it's not going to be considered a formation reaction at that point because diamond is not the standard state, and the reactants have to be elements in their standard states. Cool, now finally we've got all the standard states. Now we got to balance this thing once again. 1 sodium, 1 sodium. So there's 1 hydrogen there. We'll have to put a fraction and use a fraction there. 1 carbon, 1 carbon. And then the oxygens, there's 2 here, there's 3 here. We'll have to put a 3 halves here. And again, no way around those fractions. If you want to use 0.5 and 1.5, well, power to you, it's the same diff. But you can't just double everything through so that you don't have fractions. Because again, we can only form 1 mole of a single product and have it be a formation reaction. Cool, now if you get a question on the test that says, which of the following is a formation reaction? Cool, first thing you want to look at is the product. So look at all the reactions. If any of the reactions form more than 1 product, or more than 1 mole of a product, they're not formation reactions, cross them off. And then move on to the reactants. The reactants have to be elements, not compounds. If any of the reactions have compounds on the reactant side, those are not formation reactions, cross them off. And then once you've identified them as elements, then you got to make sure they're in their standard states. Like if this had said carbon diamond, well, that's not a formation reaction. If this had said just said H gas instead of H2 gas, that's not a formation reaction. If this said H2 liquid, again, that's not a formation reaction. So you got to have the reactants being elements in their standard states. Super important. So, but by the time you get through that, eliminating the wrong ones, you should hopefully have just 1 right, 1 left. Now, if you found this lesson helpful, the thumbs up button and a comment letting me know are pretty much the best things you can do to support the channel. And if you're looking for general chemistry practice, take a look at my General Chemistry Master Course. It includes over 1,200 practice questions. A free trial is available. I'll be sure to leave a link in the description. Happy studying.